Oh, there we are. Thank you. Very good. Yes, so to do this has required us to develop some numerical techniques and to kind of generalize approaches for applying large deviation theories when we have such complex systems. Okay, but before I get here, let's start with somewhere where everybody is comfortable. Okay. So this is a system I think we all kind of understand. If I took a macroscopic lead pipe and I put one end of it in a hot temperature bath and the other end in a cold temperature bath, I kind of know what to expect, right? In fact, I don't even need to tell you what that material was. The second law tells me that heat will flow. And more than that, it tells me which direction it will flow. Heat will flow from hot to cold. In fact, we know a little bit more, right? Fourier, almost 200 years ago, taught us that not only do we know that heat will flow from hot to cold, but how fast it will flow. The rate at which energy is transported from one end to the other depends on only one number. A material property, the thermal conductivity, the ratio of that heat flux to the temperature gradient that's been applied. And that's really very interesting, right? Independent of the geometry of that pipe, independent of how big it is, if I just know, what it's made out of, what thermodynamic state it's under, I could tell you how fast the heat will flow. And I think, already Fourier knew that this was an approximation, right? This is a perturbation theory. This is a first-order correction for generating a temperature gradient and getting a heat flow out. But it's a really good approximation, right? For macroscopic objects, the kinds of temperature gradients we can apply to them really perturb the heat carriers, the atoms and molecules, so little that they almost always respond linearly in proportion just to the temperature gradient. So really, this number describes macroscopic physics quite well. Now, there are cases where that's violated. If you really get something very extreme, you generate shocks, or you apply temperature gradients that are millions of Kelvin instead of hundreds or thousands, you can get out of that linear response regime. But those are really exotic. Right? But now let's do a thought experiment. Let's take this macroscopic object, which responds linearly. I only need to know the thermal conduction or the thermal conductivity to understand it. And let's just now shrink it 9 orders of magnitude. Okay? So instead of flowing heat through a lead pipe, I flow it through a carbon nanotube. So now immediately the scale over which I'm applying the temperature gradient is a lot smaller. And moreover, something that is immediately abundant, immediately clear, and I think anticipated from everybody here, you could tell that this is a dynamical system. If I look at a lead pipe, I don't see anything interesting. It's because macroscopically, there's so many atoms, you've just regressed to the mean, you don't see fluctuations, but microscopically, you do. So this is actually a molecular simulation. I'll show data for later of what a vibrating carbon nanotube looks like. And it moves, it fluctuates. And so immediately one thing is clear, that the heat current that we would measure is now more subtle. It's not a number, there is a distribution of currents. We have to worry about fluctuations. But more than that, the heat carriers, the phonons or the atoms and molecules, which are actually moving the heat from one side to the other, now the scales that they move and feel are not so different from the scales we're applying those gradients on. So it's quite easy actually to generate nonlinear responses. So we might have to develop a series that would tell us how the transport occurs. Maybe there are more material coefficients. And moreover, the scale over which I'm perturbing the system, or the scale over which the system exists itself, might not be large compared to those atoms and molecules, in which case these numbers might also depend on the size and geometry of the system itself. What was that? Not if you lack inversion symmetry, for example. Maybe I put a little schmutz on this side, and now I can have a K2 and a thermal rectifier. Right? Okay. So these are the sorts of things we have to confront, and so that's what I'll try to do through the talk, is how do we think about nonlinear responses, scale-dependent responses, and we'll start just by confronting fluctuations. And for a little while, I'm not going to tell you anything new, and so let's start there. So what do we know about fluctuations of things like currents in microscopic systems? Well, starting in equilibrium, we know that the probability of a current fluctuation from Onsager and others is Gaussian. That's a statement of microscopic reversibility. I don't have a net current, so it's centered about 0. And we know even more from people like Kubo that that variance is not an independent parameter. It actually tells us how the current is generated if I add a small perturbation to the system, if I do something to generate a current. So in the limit that this driving force is small, which is a statement of how close these distributions overlap, near equilibrium fluctuations we know quite a lot about. This is essentially a manifestation of Boltzmann statistics, though extended into dynamic phenomena. Only entropic or thermodynamic contributions enter into this distribution because it's just perturbed away from an equilibrium state. Okay, so what do we know away from equilibrium? Well, we know some. Actually, in the last 20 years, we've learned a lot, right? We know, for example, that there are symmetries associated with fluctuations of currents. They obey fluctuation theorems. We've heard a lot about that in the talk. For the kinds of currents I'll think about in this talk, the relevant fluctuation theorem tells me that the likelihood of generating a current in the forward direction, heat flowing from hot to cold, relative to it reversing itself, which there is a fluctuation that will do that, but it's exponentially unlikely with a factor that depends on the entropy that's produced. And for the simple sorts of non-equilibrium steady states I'll consider, that entropy is easy to write down. It's just the affinity that drives the current times the current itself. We know a little bit more than just the symmetry relations. We know asymptotics. Those are given to us by large deviation theory. We know if that current is made out of a sum of contributions that have finite correlation times, then I'll be able to break up those correlation times. They'll obey a large deviation principle. And that large deviation principle means that the distributions of currents will depend on a number that only trivially depends on time. So this is a rate function. This is a log likelihood scaled by time of the probability distribution. Okay. That's great. So we have some structure we can work with. And in fact, this large deviation form actually becomes a very useful tool, as we've heard a lot this week. For example, it turns out to be a little bit difficult often to compute the rate function directly, so one tries to compute a cumulant generating function instead. That's just a Laplace transform. I'm implicitly working in steady states here, so I've neglected the explicit t goes to infinity limit, but those should be implied throughout everything I tell you. The cumulant generating function is just the Laplace transform of that rate function. By definition of a generating function, I take derivatives with respect to counting parameters, I get cumulants. And through Laplace's method, there's a Legendre transform relationship that takes that cumulant generating function into the rate function. Okay, so that's well and good. There's nice mathematical structure in these sorts of problems and thinking about currents even far from equilibrium. But they really do contain quite a lot of information. In fact, this is a nice example of how you can just read off the mechanism by which heat is transported if you just know something about the structure of those distributions. So the rate function for two different examples of heat transport processes, one either going through a harmonic lattice in which the heat transport is ballistic, or one in which it's purely diffusive, will have different features to that rate function, that scaled probability distribution. They'll have exponential tails in the case of ballistic transport, or it'll be a perfect Gaussian if the underlying process is perfectly a Gaussian process. Here I've plotted this in such a way that the conductivity, the second derivative about that mean value, is the same, and so you can see how quickly those deviations from just Gaussian behavior grow in for the harmonic lattice, for example. And what's really nice is that for lots of simple models, you can actually compute these things. It's not easy. You have to solve, in general, an eigenvalue equation to get the large deviation function, but this is exactly solvable, and we've seen that, right? Unfortunately, it's not exactly solvable for the kinds of systems I'm interested in, these molecularly detailed models of carbon lattices or electrolytes. But this structure actually gave us a lot of direction for how we might try to compute them numerically. I won't talk a lot about this. There are experts here that invented some of these techniques. but this gives you a flavor of the sorts of methods we've brought to bear on these kinds of problems. They basically leverage the fact that this is an eigenvalue problem, and there's lots of expertise solving eigenvalue problems that we've learned by solving the Schrodinger equation. One of those techniques is a diffusion Monte Carlo. Things are even better for us because we don't have sign problems like they do when you're solving the quantum mechanical problem. So one can write down an algorithm that's analogous to diffusion Monte Carlo in the studies of large deviations. This is called the cloning algorithm. This just breaks up this expectation value for the large deviation function, spreads weights across walkers, and alternatively propagates those walkers' individual trajectories and carries weights and then branches and grows those weights. It turns out that for lots of the systems we're interested in, just this by itself kind of runs out of steam very quickly. That's because you essentially have to represent potentially exponentially large weights, and to do that correctly or accurately requires you to have an exponentially large number of walkers. This is essentially a cursive dimensionality. If I look at collections of large numbers of particle systems, that even over small times, those weights can grow very large. These are quantifications of how that behavior grows in. This is a eventual exponential scaling of the number of correlated walkers, so a measure of statistical independence and estimates of these large deviation functions. But we figured out ways around this, leveraging the fact that this underlying structure is a diffusion Monte Carlo. So if I'm in a chemistry department, I go next door and talk to people solving correlated electron problems. They say they almost never use diffusion Monte Carlo out of the box. You always have guiding functions and importance sampling functions, and we can do the same here. Turns out to develop guiding functions, you could use mean field theories. These are just importance sampling methods. What this looks like in practice is essentially a set of forces that you add to the system to help encourage it to go to those rare fluctuations. Right? You could write those down analytically and do similarity transforms on those propagators, or you could just try to let the computer learn them. So this is some work we've done recently with Wanpei here, where you try to iteratively find the best driving forces to encourage those rare fluctuations. And these actually work quite well. We can really reduce the cost, statistically speaking, of doing these sorts of calculations. So this is an example from this paper here, where you can increase the statistical efficiency of this algorithm by orders of magnitude just by giving a little guidance on how you sample these large deviation functions. Okay, so I'm happy to talk about this sort of thing offline, but this isn't really the focus of my talk. What I want to tell you about is really bringing these kinds of tools to bear on interesting systems. So I'll start just by thinking about near equilibrium phenomena. So by virtue of this large deviation function, we know it generates the cumulants, and you all know that near equilibrium, those large deviation functions, those second-order cumulants, provide response information. In fact, there's a really nice proof by Pierre Gaspard that just uses the fluctuation theorem symmetry here in its integrated form for stochastic dynamics called the Lebowitz-Spoon symmetry. Just taking this in by itself, no need to go through the complicated calculations Kubo did once upon a time, you can get essentially a Green-Kubo relationship, or an Einstein-Helflin relationship more specifically, between the response of a current to an applied field and that second-order cumulant, the variance of the current, which is also then just the second derivative of a cumulant generating function. Okay, again, this is not news to anybody, I suspect, but it actually is quite a useful recognition because exponential averages put through the procedures of importance sampling are then actually quite easy to evaluate. So for systems where the integrated correlation functions are numerically difficult to converge, this is a way to importance sample those functions. And so we've actually shown that in simple systems, like heat conduction through hard spheres or interfacial friction problems, which have long time tails, that these can actually yield statistically significant estimators of even linear transport coefficients. So what one does specifically is actually just try to compute this large deviation function directly, and then either numerically or through different estimators, measure the variance. So you could fit a curve with a parabolic, extract that variance, and then get what is, in the case of a heat conduction problem, the thermal conductivity. And by virtue of being able to tune these biasing parameters, you actually suppress the statistical errors associated with that estimate. And in a way that actually makes this quite useful. If you're trying to look at the self-diffusion of a Lennard-Jones particle, this is overkill, right? Those are correlation functions that are easy to converge. But if something slowly decays, if there's sampling difficulties because there are lots of particles, this could be a useful tool. But this doesn't tell you anything you couldn't get otherwise, just does it in a more efficient way. What we were really interested in is the nonlinear responses, the responses of systems out of equilibrium where there's not really other tools that we can use. And so to tell you how we would use large deviation functions to compute nonlinear responses, we had to develop some of that technology ourselves and some of the theory. So I'll go through that by itself first. So the first thing that I was very naive when we started this. For some reason, I thought, well, coming from equilibrium, if I know the variable's distribution function I'm interested in, I should be able to predict its response. That's true in equilibrium. If I know the whole distribution of energies, I can compute the heat capacity at any temperature. So naively, very naively, I thought, well, if you just knew the whole distribution of the currents, which you can get through large deviations, maybe I could predict the response of that current to a field. Christian especially would know that this is not true. The currents at some applied field is not just a function of those thermodynamic variables out of equilibrium. You can see that quite plainly just by unwrapping what you mean by a current under an applied field. That's an average over paths. It's a time integrated quantity. This is, by current, I mean really the integrated displacement. So that's the operator I'm trying to average, and that's the measure I'm averaging it with, which depends on that applied field. If I were to relate that measure to its equilibrium measure, if I could write that down, because I have my equations of motion, I know how to represent the probability of a path. That means I can write it down in the presence or absence of the applied field. That then ratio of probabilities is a relative action. And it's quite easy to demonstrate that that relative action has, in general, two different parts. It can be decomposed into time reversal asymmetric pieces. That will be the entropy production by definition or construction through the fluctuation theorem. But in general, there are other parts. There are time reversal symmetric parts, which then tells you immediately that if I want to know only equilibrium information in the absence of an applied field, in order to predict the current at any finite field, I'm going to need to know something about both time reversal asymmetric parts, the currents, and things that have nothing to do with the currents. Okay, so this in general is hard to say something about. I'm going to focus throughout this talk on Langevin processes, where for linear forces or forces that are somehow linear combination of the underlying molecular degrees of freedom, this actually takes a very simple form. The time reversal symmetric part of that relative action is something that is linear in the field times a time integrated activity. This is the frenetic contribution, as Christian would have taught us. And in general, there's a second order process, or a piece that goes quadratically in the applied field. But what's nice about that is that it's a constant. In fact, the applied field enters in squared times a number, which is essentially parameterized by my Langevin process, the response of the system to in a non-interacting limit. Yeah. Gersinoff. That's just taking a stochastic process and reweighting it. So it is just this trick here. But this tells you, so Gersinoff, because there's a Gersinoff theorem, tells you when this is going to be okay. In these Langevin problems, as long as you aren't messing with the scale of the noise, just adding drifts, you know that these probability distributions are continuously overlapping. All right, so then this actually gives us a nice structure. We have a time-integrated piece that's symmetric in time, the activity. We have an entropy reduction part. Because this additional piece is just a constant, you can then get a very simple equation for the current at any applied field as just a reweighted average from equilibrium that knows something about both the thermodynamic cost to generate a current as well as the frenetic cost to generate that current. This is essentially a rewriting of this constant term, which is a reflection of conservation of norm of this Gaussian process. That's actually really nice. So I can predict the currents arbitrarily far from equilibrium just by knowing equilibrium information. That sounds a little too good to be true, and there's some cost to doing this. It's not universal in the sense that it's not just thermodynamic information that enters. I have to know something about the dynamics. That's encoded or encapsulated in these time-integrated symmetric contributions. But the fact that it has this sort of exponential form means we could use the technology of large deviations to then express it. So in this case, what we do is we write down a large deviation function that's joints in the current fluctuations as well as the frenetic contributions. So this activity and the current, they have two Laplace, they're counting variables that enter into this definition of the joint large deviation function. And from that previous reweighting expression, there's an asymmetry between that large deviation function out of equilibrium under an applied field to that in equilibrium, no applied field, with some additive constant there. So again, knowing the joint fluctuations of two variables then is sufficient to tell me the full non-equilibrium response of the system. And because I can calculate these numerically, this is a useful tool. Just to show you how this would work, in a simple model of a Brownian ratchet, something that has that second order coefficient finite because it lacks inversion symmetry, this is a one-dimensional diffusion problem. I could, through solving that eigenvalue problem numerically, get the exact joint large deviation function. It looks like this in the space of the current counting parameter and the activity counting parameter. And by evaluating that large deviation function at a particular symmetry point, so when both of those counting variables are equal to minus beta times the applied field, I can get the whole current voltage relationship. And these are all exact statements, so not surprisingly, this agrees exactly with numerical results where you measure the current directly, right? Which is easy to do in this system, more difficult to do in the molecular systems. Okay, so this is the framework we're going to use. So in the last, let's see, when do I need to, I have about, 30 minutes? Yeah. Good. I will tell you two little vignettes where we've applied this, first in low-dimensional heat flow problems, carbon lattices, and then in nanofluidics. Let's start with the heat flow problems. So this was motivated because I have colleagues across the road that have actually measured heat flow in low-dimensional lattices, both carbon lattices and boron nitride lattices. These are multi-walled nanotubes, so they would argue that that doesn't matter so much. And what they found is general violations to Fourier's law. Again, to them, this was maybe surprising. To all of you studying low-dimensional lattices for a long time, maybe not so. Indeed, lots of those calculations for simple models, FPU, chain-type models, have clarified that there's more or less two universality classes if you have anomalous heat transport that are characterized by different anomalous scaling coefficients for how the thermal conductivity varies with the length of that tube. So these universality classes come with exponents that are either a third or a half, depending on features of the underlying potential and what conservation laws are present, in addition to translational invariance, which is required. So then we can go and ask, if we can come up with a molecularly detailed model, which class does it fall into? And so what we've done is we've got a model. It's complicated. The interaction potential is derived from ab initio calculations, fit to some functional complicated many-body form, but provides a very good description of the relevant phonon degrees of freedom or vibrational degrees of freedom, lattice degrees of freedom. And we can ask for a generic response for the heat current. Heat current is the time-integrated heat flux. The heat flux we'll choose is that which goes into Langevin reservoirs. These are actually periodic systems, so those reservoirs are stuck kind of halfway through the systems on either end. We'll consider both graphene as well as carbon nanotubes. This is a specific 10 by 10, I think, weaving of a carbon nanotube with a diameter of about 1.5 nanometers. And we can ask, if we compute this response coefficient over molecular dynamics trajectories, which we can evolve in time. Those don't look all that exciting. These are just vibrations, but that's what they look like. We can ask, are there scaling functions that will collapse those as we vary the length? Easy enough. So these are the results. So this is the probability minus the log of the heat current per time. So this is a large deviation sort of scaling for different size nanotubes. So the color bar here tells you that we're going from between tens of nanometers to about a micron in length, represented on a computer for a nanotube or a graphene sheet. And we could first do these calculations just at equilibrium, measuring the fluctuations of the heat current that goes through those Langevin reservoirs. And this is what they look like. I must tell you that I was really bummed when I saw this because those are incredibly Gaussian. I was really hoping to see some more interesting features, but these are Gaussian to a very good extent. This 30 betrays the fact that this is divided by time. The time we took here is some tens of picoseconds, so these are incredibly rare fluctuations, and yet they're Gaussian. It's just missing, yeah. We kept getting Gaussian, so we stopped. So they're Gaussian both for the nanotube and the graphene sheet, but what is kind of interesting is that if I write down a scaling form that asymptotically goes like L to the 1/2 for the tube, or logarithmically for the sheet, these collapse. That tells you immediately what the anomalous transport looks like. Right? So those are equilibrium calculations. We can also do the explicit non-equilibrium calculation, applying a temperature difference, measuring the heat flux. Because those fluctuations are Gaussian, are incredibly linear. So over a broad range of applied temperatures, you have linear response. Those slopes then are related to the thermal conductivity. This is the total heat flux through those reservoirs. And again, if we use those same scaling relationships, they collapse. And you could argue maybe for the small tubes, you see small deviations from that linear response, but it's actually quite hard to say when you should stop seeing the Kapitsa-like resistance for the boundary between the reservoir and the actual carbon nanotube. So I suspect that these deviations are really just from that. And the fact that those same scaling relationships hold is a nice consistency check that whether or not we're in equilibrium or out of equilibrium, we see the same sort of anomalous behavior. So just summarizing that, if you then just pick off those conductivities, plot them as a function of length for the tube or for the sheet, those do look to a good extent either in equilibrium or in the non-equilibrium steady states, like they diverge like L to the 1/2, or logarithmically for the graphene sheet, so a two-dimensional heat conduction problem. Now, it's a reasonable argument to be made that maybe I haven't gone far enough in length. Maybe this behavior will change asymptotically. These are already a micron. So for all intensive purposes, there's a huge domain of lengths where they behave like this. So all of you probably understand where this comes from in terms of a stochastic process. If you have an anomalous exponent of 1/2, that tells you that this is really a Levy process. This is a Levy walk. And you can confirm that those Levy walk statistics actually hold. You can look at energy spreading by localizing some amount of temperature at the middle of the nanotube and letting it propagate. Or there's a really nice result for Levy walkers that have open boundaries where you can actually compute what is the profile of those Levy walkers. In this case, this is the heat that's moving around. And those profiles actually fit much better than just a Fourier's law. There's persistent deviations at the boundaries that turn this into something more sigmoidal than something purely linear. Again, these little jumps here are the Kapitsa resistances. So it seems all internally consistent that in carbon, for a realistic model, heat transport is anomalous, and the universality class it falls into is that the heat conduction diverges like L to the 1/2. So now let's switch to ionic transport. So again, this is motivated from experiment. There are experiments, especially by Bouquet's lab in Paris, which are making devices where you're able to actually measure the flow of ions and water across nanometer-sized channels. And so again, the standard hydrodynamics you might expect to be able to apply starts to break down. And if for no other reason than surface to volume ratios are becoming large, friction contributions are becoming important. And one of the most interesting results that they've found recently is a violation of Ohm's law. Ohm's law tells you that the ionic current is proportional to the applied field with a constant proportionality. That's the ionic conductivity. In general, that ionic conductivity might itself be a function of the applied field. And a reflection of that breakdown of Ohm's law is found by looking at the mobility of ions as a function of the applied field, here expressed as a voltage drop across these slit pores, which is a strong function of that applied field. Connoisseurs of these sorts of things will note that there are finite derivatives at zero, which is something that time reversal symmetry would forbid. This is actually the mobility measured on top of an underlying pressure-driven flow, which is why there is some flow there to begin with. Again, we could use the tools that we've developed to work out molecular models and study this sort of field-dependent conductivity. And so we do the same sort of game I've just expressed. So I can write down a response coefficient at an arbitrary applied field, which is just how the current changes with that field. So these are all differential conductivities. The ionic current in this case is a time-integrated velocity of a particle or an ion times its charge. I can work out models. Again, these are Langevin models, either overdamped or underdamped, depending on whether or not the solvent is there explicitly, that look kind of like this. So the big yellow spheres are chlorides, the little green spheres are sodiums, and they're moving under the action of an applied field. There's water there solvating them in explicit solvent cases. We also studied implicit solvent cases where the ions are the only things present. And so again, computing the rate function, the log of the probability of observing a current divided by time, here I got a more exciting result. Some of these are non-Gaussian. So I'm showing you here 4 different systems. These are all implicit solvent. One is a simple electrolyte, sodium chloride. Both have single positive or negative charges. One is a divalent cation, magnesium 2+ with 2 chlorides. And they are either solvated implicitly in a high dielectric, something like a good solvent like water, or a poor solvent that has a dielectric constant of 10. The high dielectric constants, think water, well, you all know water dissolves salts. That means that those electrolytes are strong. They're largely free to diffuse. The correlations between those ions are not strong. And as a consequence, their fluctuations of currents are Gaussian. Again, that is just central limit theorem behavior. It tells you that the correlations are not important. However, in the low dielectric environment, you see marked deviations from Gaussian behavior. Central limit theorem tells you I still have to have a Gaussian near the mean, but you see that there are fat tails showing that the likelihood of seeing a large current, either in the positive or negative direction, this has to be symmetric about the origin, are much more likely than you would have expected. Yeah. Convex. It is convex, but you're very right. It looks like it's almost not. The signature of that will be a little bit more clear in the next slide. Okay, so indeed, there's non-Gaussian behavior. Maybe there's a little bit of a shoulder. Maybe it even turns over. But suffice to say that when you have non-Gaussian statistics, you have to have nonlinear responses. And so if we are able to evaluate that joint large deviation function in the current and the time reversal, the time symmetric part of the action, I should go back a slide and actually tell you what that is, because it's important in this part. In this part, the time integrated activity for this Langevin model is actually quite appealing as a nice interpretation. It's just the charge-weighted intrinsic electric field that acts on the ions. So the fluctuations of that intrinsic field from the ions interacting with each other times 2 factors of the charge squared and divided by the friction from that implicit solvent, correlations with this variable and the current will generate important contributions to the nonlinear response. Okay, and indeed, if we compute that joint large deviation function in the current and the activity, we're able to predict the nonlinear responses. So this is the ionic conductivity as a function of the applied field. For those Gaussian strong electrolytes, you have no field dependence. And in fact, this is normalized such that this ideal conductivity is the Nernst-Einstein conductivity. It's the conductivity associated with free charges. So that conductivity is saturated there. It is suppressed relative to that for the weak electrolyte systems. But as I increase the field, I start ripping those ion pairs apart, and I go to that ideal Nernst-Einstein limit. This is a conductivity. It has to have a field dependence that is initially quadratic, which is why it looks quadratic. It's symmetric about the origin. This is an inversion symmetric system, so pointing the field this way or that way doesn't matter. There is both data as well as solid curves. The data are actually from explicit non-equilibrium simulations where we just apply a field measure the current. The curves are computing this large deviation function just in equilibrium and then doing this reweighting trick. So we can get the conductivity as a continuous function of the applied field. All right. We can get a little bit more mechanistic insight as to what is a reason for this nonlinear response by actually looking at the correlation functions that determine it. So the conductivity away from equilibrium, so measured in a non-equilibrium steady state in the presence of an applied field, has 2 contributions. It has a current-current correlation function. That's the piece Kubo would have told us about. And it has a current activity piece, a piece that Christian would have told us about. Indeed, both are important. So for at 0 applied field, this is a equilibrium system. Time reversal symmetry sets that to 0. So I only have to worry about the current-current correlation. Summing those 2 up gives me that dashed curve. Out of equilibrium, however, there's a suppression of the current, or there's an increase of the current-current correlation and a anti-correlation between the intrinsic fields that the ion pull on other ions with and the currents that try to go in the direction of the field. That's a dynamic picture of what's happening. Essentially, the ion tries to displace, and there's a restoring electric field that becomes weaker and weaker as I push the system further and further out of equilibrium. There's a slightly more spatially local picture associated with that mechanism, and it's kind of fun to say this here. This is known as the Onsager-Wien effect, though this is not for the city, it's for Wien, who measured these things. Onsager, a long time ago, worked out a theory with his student Wilson for how that conductivity should change as a function of the applied field. This is in the dilute limit, where you can essentially use Debye-Huckel theory. Their prediction is in blue. It's essentially a prediction for how the pair correlation function changes, deforms, under the applied field. And it doesn't work all that well. So it actually predicts an anomalously negative conductivity. This is essentially because even at a 1 molar solution, it's outside of the dilute solution conditions that it's valid for. The dashed red line is the Nernst-Einstein relationship. And in this case, this is a slightly higher concentration than what I showed you before. You do have that bump. So this goes to Wanpei's question. If you had a non-convexity in those current distributions, that's a signature potentially of a phase transition, especially if that non-convexity grows in with system size. This doesn't diverge, though I was talking with Rob about this earlier this week. I suspect this might be a reflection of a laning transition that one can see if you increase the density of these ions. All right, just to show you why this actually fails, so you can compute analytically the deformation of this pair distribution function with the applied field in the Debye-Huckel limit. That has a nice expression here. The Debye-Huckel length kappa enters in. It's a dipolar response, as it must be at first order, and has factors out in front. This is the plot of the change in the charge distribution with the applied field either predicted from Onsager-Wilson theory or what we measure explicitly in simulation. And you can see that the agreement is not perfect. There's an excess of ion pairing that just isn't captured in the analytic theory. Okay, so just to kind of wrap up, we've also studied this in explicit solvent. Here we find that the explicit solvent adds a significant friction that really destroys the nonlinear responses. You essentially, even in a weak electrolyte, if you ignored the solvent, would have some quadratic response. In the presence of the solvent, the friction is high enough that you stay near equilibrium, and thus the conductivity is a constant function of the applied field. You can beat that by actually asking for the conductivity near a surface, and if that surface is atomically smooth, you have a significant slip, a lower friction, and it's easier to drive nonlinear responses, as we've shown here. And those nonlinear responses depend on how much slip there is, so they change if I'm doing this near graphene or hexagonal boron nitride. Okay, so just to conclude, I've shown you some numerical techniques and some studies of transported nanoscale systems where we use the structure, mathematically speaking, of large deviation functions, both to gain insight as to why those nonlinear responses exist, as well as a practical tool to compute them. And I've shown you that in two cases, heat transport and in a liquid for ionic transport. I should end by thanking the people who did this work. All of these studies were initialized by my former PhD student, Chloe Gao. Anthony and Philip have taken on the ionic conductivity problem, so the slip-related work are their efforts. The ionic conductivity was done in close collaboration with my friend Benjamin Rottenberg, and the numerical techniques that we've developed to actually deploy in these sorts of systems are really the product, first of Avishek Das, early work with a former collaborator, Garnet Chan, who's a quantum chemist, so knew these, was very useful in knowing these relationships, and most recently with Wan Pei. These are the funding, that's the group, and I'll take questions.